Here's a more complex pulley problem. Okay, so imagine that we have a inclined plane like so, and something sticking out here, and a pulley here. Okay, and this pulley is massless, and frictionless. Okay, and then we have a mass hanging off that pulley, mass M2, let's say, and we have this pulley attached to another disk. Which rolls without slip here. Okay, rolls without slip, and this disk itself has mass M, radius R, okay, and that's the basic premise of the problem, and you're asked to compute the acceleration of M2 in terms of all the given quantities, in terms of M, R, M2, G, and really I suppose that's about it. Okay, so that's what we need to compute. The first step, of course, is draw a free body diagram. This is the solution. Okay, so let's draw a free body diagram of the disk first. So this is a uniform disk. So its IG is basically M R squared by 2. Let's say that's given as well. You'll be given that in your exams. Okay, so the free body diagram is, that's the disk. There's going to be a normal reaction there. And there's going to be some kind of a friction force, F, on the surface. And then there's the rope that's pulling on it. So we have a tension T. We have the center of mass there. And we have gravity mg due to that, or m1g perhaps. What else? What other forces do we have? That's it, really. Okay, for that particular disk. So this is this disk. Okay, so that's the disk in red. For the pulley itself, for this pulley, because it's massless, well, all we have is the fact that this tension on this rope is equal to the tension on this side of the rope. If this had mass and it moved without slip, then you would have the tensions potentially different. But if the pulley is massless and the thing is frictionless, then you have the two tensions equal. Okay, so the two tensions are equal, so we can really skip the pulley free body diagram. Now we can draw the mass free body diagram M2. So for M2 it's going to look like this, of course. Right. Yeah, so you can draw the pulley free body diagram as well if you want. T, and then that's going to be some reaction forces here, which we can leave unlabeled. There's going to be some unknown reaction forces, but we don't really care. Okay. Okay, so these are the primary primary free body diagrams. Okay, now we only have a couple of principles. Well, actually three different principles. Principle number one is sum of forces equals ma. Another principle is sum of moments equals I alpha if you're taking moments about g. And then we have variants of that. And then the third principle is to potentially use the fact that this thing rolls without slip. Okay, so let's actually define sign conventions for everything. So sign conventions. So we have the system like so. Let's call this acceleration going upward A2. Let's call the acceleration of this thing going this way A1. And then let's call this angular acceleration alpha. Okay. These are the sign conventions for the accelerations. First, let's dispose of rolling without slip. Okay, we can do this sort of many times, so to speak. So we have this object, this is g, if this is omega, and this is v, and this is I, let's say, for a moment. Then this point P has velocity equal to 0, so Vp equals Vg plus omega k cross minus r j, where again this thing is rp with respect to g, and vg is, so this is 0 equals, vg is actually minus vi, and then minus r omega, k cross j is minus I. So we have v plus minus v plus r omega equals 0, or v equals r omega. So that's one way to think about it. Another way to think about it is basically it's rotating about point P. This is a disk rotating about point P because that's the instantaneous center of rotation. So if that's the instantaneous center of rotation, V equals R omega. Okay, that's another simple, perhaps simpler way of thinking about the same thing. Instantaneous center of rotation, this V equals R, which is this distance times omega. Okay, so that's what we get for rolling without slip. And then the other equations are essentially going to be F equals ma for this, F equals ma for this, and potentially sum of moments equals I alpha for this. Okay, so let's work that out. Let's first do F equals ma for this. For M2, we are going to have essentially M2A2 equals the tension force minus M2G. So that's going to be equation number 2. For the disk, and then for the disk, we can do two versions. So of course we can replace mg by mg cosine theta, mg sine theta, where this thing is theta. Okay. So let me redraw this free body diagram out here with that decomposition. We have n, we have f, we have mg sine theta, we have mg cosine theta, we have the tension T, and that's it, right? So we replaced this mg with mg cosine theta, mg sine theta. Now we can do F equals ma. Let's call this direction J. Let's call this direction I. So along I, we've defined A to be in this direction. So what we're going to say is essentially ma1 equals mg sine theta minus t minus f, and that's it. Along J, we have n minus mg cosine theta, sum of all forces, equals mass times acceleration, the vertical direction, which is 0, perpendicular to the plane. Okay, that's equation 4. And we really don't care about this equation because, well, if the object was slipping, the normal reaction could be of interest. But if the object is not slipping, as we've discussed, the friction force is solved for by essentially solving all these equations simultaneously. So we will not have to use something like mu n or something like that to determine the friction force. We will have to use mu n only to see perhaps if it is slipping, if the friction force is too high. Okay. Now, okay, so we have all these equations. We need one more equation, which is sum of moments equals I alpha, perhaps for this system. Now, what point about which we want to take that moment? Let's actually, so let's call that G, let's call that point P. We can do any of the either G or P. Let's try P, or G, doesn't matter. Let's do G, I guess. Sum of moments about G equals IG alpha. Okay. As we've discussed, IG is equal to mr square by 2 alpha k. Sum of all moments about G. N passes right through G, does not have a moment. F does have a moment. It's F times R, and it's in the anti-clockwise direction, so it's F R K. T has a moment about G. It's T times R, and that's in the clockwise direction, so it's got a negative sign. And mg sine theta has no moment about G because it passes right through it, nor does mg cosine theta because it passes right through it. So these are the, this is actually the moment. Let me actually pull this closer to this equation. Equals mr squared by 2 alpha k. And we can sort of cancel the k out. All these moment equations and all these problems is just going to be in the k direction, so we can just drop the k's. So this implies f minus t times r equals mr squared over 2 alpha. We can cancel the r's, so we get f minus t equals m r alpha by 2. By the way, I said v equals r omega. This actually implies a1 equals r alpha. Okay, this a1 equals r alpha because that's the derivative of this equation. Okay, so because a1 is r alpha, we can relate those things. We can plug that in here. So let's plug that in here. By the way, let's number this thing, equation number 5. Let's actually, before we substitute this thing, let's think about something. Let's think about how many equations we have and how many unknowns we have. What are the unknowns? A1, alpha, t. So let's write that down. A1, alpha, T, the tension, A2, which is actually what we want to find, the friction force, and the normal reaction M. So we have actually six unknowns, and we have 5 equations so far. We need one more equation to be able to actually solve for everything. And what is that equation? Let you guys think about it for a second. Okay, the equation is actually the fact that this pulley is connected to this point. This pulley, this mass is connected to this point. Okay, now here's where things become a little subtle. If this mass was connected to the center of this disk, then this A2 will be the same as this A1. Okay, if it was connected to the center, but it's connected to the topmost point. Okay, recall that because this this is the instantaneous center of rotation, this point has velocity v, and this point has actually velocity 2v. Okay, because it's 2r times omega. This point, the topmost point, actually has velocity 2v. Similarly, if you look at the acceleration of this point along this direction, it's going to be 2r alpha as opposed to r alpha. Okay, so let's actually denote that point by something. P, I don't know. Let's actually do that here. Need one more equation. It's a relation between A2 and alpha. Okay, so the way that works is if the tangential component of this, if this point is Q, and basically we have this thing connected to M2, which is going up with A2, the tangential component of this point's acceleration, let's say, is AQ. AQ is going to be 2 so if we say the acceleration is AQ and the velocity is VQ, we'll basically have VQ equals 2R omega, because it's as if it's rotating about this point, and this is basically 2R. So, and AQ, the tangential component of that, the component perpendicular or parallel to the ground, is basically 2R alpha. And basically this means, because this string is not slipping against this disk, AQ will be equal to A2, which means that 2R alpha equals A2. Okay, so this is actually the desired sixth equation. Again, recall, if this thing was connected to G, then A2 will just be equal to AG or A1. But because it's connected to the top point, it's actually a different acceleration. Okay, so that's the sixth equation. Okay, let's put this all together and solve for what we want to solve for. I think we've been asked to solve for A2. So let's do that. So we can essentially use 6 to replace alpha here, and then replace A1 here, and then essentially solve for eliminate F. Okay, so let's do that. Use so alpha equals A2 by 2R. So that's basically the same as 6. Plug that into 5. To give F minus T M or alpha divided by 2, and that gives us M or A2 over 2R. The R's get cancelled, so we have M A2 by 4. So what do we have? F minus T equals M A2 by 4. Let's call that equation number 7. Now let's, well, we have this equation. A1 equals R alpha. We just noticed that A2 is 2R alpha. So use 6 in equation 1. A1 equals R alpha equals R A2 by 2R, and basically A2 by 2. So A1 equals A2 by 2. Let's call that 8. And let's use 8 in this equation, equation 3. So use 8 in 3. Let's rewrite what 3 is. 3 is MA1. MA1 equals mg sine theta minus T minus F. That's the equation 3. So we have MA2 by 2 by essentially using this relationship equals mg sine theta minus T minus F. Okay, let's call that equation number 9. So what do we have? We have equation number 7, which has A2, F, and T. Equation number 9, which has A2, F, and T. So we have two equations in A2, F, and T. And then we want to use this one as well, which is equation number 2, which is something that we have not used. Let's write that down. To equation 2 is basically m2 a2 equals t minus m2g. So we have these three equations: equation 9, equation 7, and equation 2. We can eliminate t from equation 9 and 2 by adding them. So let's add 2 plus 9 gives m a2 by 2 plus m2 a2 equals mg sine theta minus t minus f plus t minus m2g, and the t gets cancelled. So we have a2 m over 2 plus m2 equals mg sine theta minus f minus m2g. Let's call that equation number 10. And then equation this equation let me back up a little bit. Yeah, so let's actually eliminate t instead of f instead of t, I suppose, because we have an equation that just has t. So instead of so this is an equation that just has f. Ideally, we want another equation that just has f so that we can sort of cancel out the f. So what I'm going to do instead is go back a little bit, and instead of what I'm going to do is use equation 9. What I'm going to do is use equation 9. So equation 2 already has just t and a2. What I'm going to do is use equation 9 and equation 7 to eliminate f between the two of them, so that we get another equation that just has a2 and t, and then we can use equation 2 along with that to essentially solve for a2 and, if you want, t as well. Okay, so what I'm going to do is erase the stuff. Okay, magic. So how do we eliminate F, the friction force, from equation 7 and equation 9? Let's just rewrite equation 7 like this: ma2 over 4 equals f minus t. So that's the same equation 7, just interchanged left and right. So let's now add equation 9 and equation 7, and we should be able to eliminate f. So equation 7, let me erase equation 2 for now as well from here. Equation 7 is going to be ma2 4 equals f minus t. That's equation 7. Add. We get m a2 over 2 plus m a2 over 4 equals mg sine theta minus t minus f plus f minus t. So what do we have here? So we have ma2 half plus a fourth is 3/4, equals mg sine theta minus 2t. So let's call this equation number 10. Now we have two equations in two unknowns, a2 and t here, and all the way up here we have another equation, a2 and t. So let me bring this equation down there. m2a2 equals t minus m2g. m2a2 equals t minus m2g. That's equation 2. So now we are looking to solve for a2. We need to eliminate t. We have these two equations. So let's actually multiply equation 2 by 2. So we have 2m2a2 equals 2t minus m2g. And now we can add with 10. So equation 10 plus 2 times, well, you can call this 11 if you want. So we just have 10 plus 11. So we have 3 over 4 ma2 plus 2m2 a2 equals mg sine theta minus 2t plus 2t minus m2g. These get cancelled. So what do we have? We have 3m by 4 plus 2m2 a2 equals mg sine theta minus m2g, or a2 equals mg sine theta minus m2g divided by 3m by 4 plus 2m2. Okay, so I know that we solved these problems using symbols as opposed to numbers, but you can imagine that we give you numbers for all these quantities, and some of the solution becomes much simpler. So on the exam, we will likely just give you numbers for all these things so that the solution is somewhat simpler. Okay, but that's basically the answer. And that's it. If we want, we can go back and solve for the friction force, which will not be some friction coefficient times normal reaction, because we've assumed that things are rolling without slip. And I guess that's that. If you want to know if the object slips, then we can go to see so if you want to know if the object will slip, to see if the disk will slip, what you can do is solve for f and check whether f greater than mu times n. If yes, slip. If no, no slip. This is not relevant to this particular problem because we've told you that it's not slipping. But if you're asked, hey, we are applying these forces, is the object going to slip? What you would need to do is assume that it will not slip, then set up all these equations, solve for F, the friction force, and then check whether it is greater than or less than the static friction, the maximum static friction. So that's how you would check whether the disk will slip. But in this particular case, we've just given you that the disk does not slip. Okay, so that's it for this problem.